Dear students, today we are going to discuss about coplanar lines. Now, two or more lines are called coplanar if they lie on the same plane. So, condition for two lines x minus alpha upon L is equal to y minus beta upon M is equal to z minus gamma upon N, and x minus alpha dash upon L dash is equal to y minus beta dash upon M dash is equal to z minus gamma dash upon N dash to be coplanar is that determinant of alpha dash minus alpha, beta dash minus beta, gamma dash minus gamma, L M N, L dash M dash N dash is equal to 0. So that means if this condition is satisfied, then these two lines are coplanar, means these two lines lie in the same plane. An equation of the plane which contains both the lines is given by determinant of x minus alpha, y minus beta, z minus gamma, L M N, L dash M dash N dash is equal to 0. Let's take few examples. First example, show that the lines x plus 1 upon minus 3 is equal to y minus 3 upon 2 is equal to z plus 2 upon 1, and second line is x upon 1 is equal to y minus 7 upon minus 3 is equal to z plus 7 upon 2 intersect. Then we have to find out the coordinates of the point of intersection and equation of the plane in which these two lines lie. Let's take the first part. Suppose that first line, this is equal to r, and for second line this is equal to r dash. So from here we have x is equal to minus 3r minus 1, y is 2r plus 3, and z is r minus 2. So any point on line 1 is minus 1 minus 3r, comma 3 plus 2r, comma minus 2 plus r. Similarly, any point on the second line is r dash minus 3r dash plus 7, 2r dash minus 7. Now if these two lines intersect, then for some value of r and r dash, these two points should be same. So the two lines will intersect if these points are the same for some value of r and r dash. That means minus 1 minus 3r is equal to r dash, 3 plus 2r is equal to 7 minus 3r dash, minus 2 plus r is equal to minus 7 plus 2r dash. So we get these three equations. Now if we solve any two of these equations, we get r is equal to minus 1 and r dash is equal to 2. Now these values of r and r dash will satisfy the third equation, and so we put r is equal to minus 1 here, or r dash is equal to 2 here. So from both of these we get the same point. Coordinates of the point of intersection is given by 2, 1, minus 3. And to find out plane which contains these two lines, we make use of this formula. Determinant of x minus alpha, y minus beta, z minus gamma, L M N, L dash M dash N dash is equal to 0. So therefore we have, in the first row we shall have this x plus 1, y minus 3, z plus 2. In the second row we shall have minus 3, 2, 1, and in the third row 1 minus 3, 2 is equal to 0. And if you simplify it, we get it as x plus y plus z is equal to 0. Let's take second example. Prove that the lines x minus 1 upon 2 is equal to y minus 2 upon 3 is equal to z minus 3 upon 4, and x minus 2 upon 3 is equal to y minus 3 upon 4 is equal to z minus 4 upon 5 are coplanar. Also find their point of intersection. Now as done in the previous example, we take this is equal to r and this is equal to r dash. So any point on line 1 is 1 plus 2r, 2 plus 3r, 3 plus 4r. Similarly, any point on second line is 2 plus 3r dash, 3 plus 4r dash, 4 plus 5r dash. So if these two lines are coplanar, means these two lines intersect, so therefore for some value of r and r dash, 1 plus 2r is equal to 2 plus 3r dash, 2 plus 3r is equal to 3 plus 4r dash, and 3 plus 4r is equal to 4 plus 5r dash. Solving any two equations, we get r is equal to minus 1, r dash is equal to minus 1, which will satisfy the third equation. So therefore put the value of r here or r dash here. So we get the point of intersection as -1, -1, -1. Now in the two examples which we have discussed just now, equation of both the lines are in the symmetrical form. Now suppose one line is in the symmetrical form and the other line is in the unsymmetrical form. Then how do we do the problem? So show that the lines x minus 4 upon 1 is equal to y plus 1 upon minus 2 is equal to z upon 1, and 4x minus 5 plus 5z minus 7 is equal to 0 is equal to 2x minus y, 5y minus z minus 3 are coplanar. Now we know that two lines are coplanar if they lie in the same plane. Now equation of the plane passing through line number 2 is given by 4x minus y plus 5z minus 7 plus lambda times 2x minus 5y minus z minus 3 is equal to 0, which can be written as 4 plus 2 lambda into x minus 1 plus 5 lambda into y plus 5 minus lambda into z minus 7 plus 3 lambda is equal to 0. Now this line number 1 will lie on this plane provided these two conditions are satisfied. Number 1, the point 4 minus 1 comma 0 satisfies the equation of the plane, and second thing is that the direction ratios of the plane passing through this line number 2, direction ratio the normal to the plane passing through this line number 2 is perpendicular to the line, this line. So let's take the first condition. Point 4 minus 1 0 satisfies this equation. So put x is equal to 4, y is equal to minus 1 and z is equal to 0. So we have 4 plus 2 lambda into 4, here it should be 4, minus 1 plus lambda into 5 lambda into minus 1 and plus 5 minus lambda into 0 minus 7 plus 3 lambda is equal to 0. So from here we will get the condition 10 plus 10 lambda is equal to 0. And second condition, direction ratios of the normal to this plane are 4 plus 2 lambda minus 1 plus 5 lambda and 5 minus lambda. So normal is perpendicular to this line. So therefore 4 plus 2 lambda into 1 minus 1 plus 5 lambda into minus 2 plus 5 minus lambda into 1 should be equal to 0. And from this equation we get 11 plus 11 lambda is equal to 0. So from both of these equations we get the same value of lambda, which is minus 1. So therefore two lines are coplanar. Show that the lines x plus y plus z minus 3 is equal to 0 is equal to 2x plus 3y plus 4z minus 5 and 4x minus y plus 5z minus 7 is equal to 0 is equal to 2x minus 5y minus z minus 3 are coplanar. Now in this case both the lines are given in unsymmetrical form and we have to find the plane in which they lie. Now what we do here is we convert both these equations into symmetrical form. There is a shortcut method also, we will be discussing in the next example. So if we convert first equation into symmetrical form, we get x minus 4 upon 1 is equal to y plus 1 upon minus 2 is equal to z upon 1. Similarly, second equation can be written as x minus 11 upon 7 divided by 13 is equal to y upon 7 is equal to z minus 1 upon 7 divided by minus 9. So as done in earlier example, we put this is equal to r, this is equal to r dash. So any point on line 3 is 4 plus r, minus 2r, minus 1 and r. Any point on line 4 is 13 r dash plus 11 by 7, 7 r dash and minus r 9 r dash plus 1 upon 7. Now if these lines are coplanar, then for some value of r and r dash, 4 plus r should be equal to 13 r dash plus 11 upon 7, minus 2r minus 1 should be equal to 7 r dash and r is equal to minus 9 r dash plus 1 upon 7. So solving any two of these equations, we get r is equal to minus 10 upon 11 and r dash is equal to minus 9 upon 27. So put the value of r here or r dash here, we get point of intersection as 34 by 11, 9 by 11, 10 by 11. So this is the point of intersection of the lines given in unsymmetrical form. Now to find an equation of the plane in which these lines lie is given by, in the first row we shall write x minus 4 y plus 1 z, in the second row 1 minus 2 1, and in the third row 13 7 minus 9 should be equal to 0. So if we simplify it, we get x plus 2y plus 3z is equal to 2. Now if we just want to show that the lines are coplanar when the lines are given in unsymmetrical form, we make use of these results. What is the result? Lines a1x plus b1y plus c1z plus d1 is equal to 0 is equal to a2x plus b2y plus c2z plus d2. This is the first line in the unsymmetrical form. And the second line is a3x plus b3y plus c3z plus d3 is equal to 0 is equal to a4x plus b4y plus c4z plus d4. This is second line in unsymmetrical form. So these two lines are coplanar if determinant of a1, a2, a3, a4, b1, b2, b3, b4, c1, c2, c3, c4, d1, d2, d3, 4, d4 is equal to 0. If this determinant is 0, that means these two lines are coplanar. Let's take one example. Show that the line of intersection of the planes 7x minus 4y plus 7z plus 16 is equal to 0, 4x plus 3y minus 2z plus 3 is equal to 0 is coplanar with the line of intersection of x minus 3y plus 4z plus 6 is equal to 0, x minus y plus z plus 1 is equal to 0. So a1 is 7, b1 is minus 4 and so on. So the given lines are coplanar if determinant of, in the column you can write 7 minus 4 7 16, 4 3 minus 2 3, 1 minus 3 4 6 and 1 minus 1 1 1 is equal to 0. If this determinant is 0, then these two lines are coplanar. So how do we solve this determinant? This is 4 by 4 determinant. We have got minus 1 here, plus 1 plus 1 plus 1. So r1 plus r2, r3 plus r2, r4 plus r2. So if we do these three operations, we get this is equal to 3 7 minus 2 0, minus 4 3 minus 3 minus 1 3 1 1 0 and 12 6 6 3 0. Now expanding with respect to this minus 1, this row, expand with respect to this column. So because these three entries are 0, so we got minus 1 into 3 7 minus 2 3 1 1 12 6 3, and if we expand this comes out to be 0. So therefore the given lines which are given in unsymmetrical form are coplanar. Let's take last example. Prove that the lines x upon alpha is equal to y upon beta is equal to z upon gamma. Second line is x upon a alpha is equal to y upon b beta is equal to z upon c gamma. And third line is x upon l is equal to y upon m is equal to z upon n are coplanar if l into b minus c upon alpha plus m into c minus a upon beta plus n into a minus b upon gamma is equal to 0. So far we had two lines. Now here we got three lines, and we are sure these three lines are coplanar if this condition is satisfied. Now from equation of the lines you can observe that all the three lines are passing through the origin. So all the three given lines pass through the origin O, and hence lines are coplanar if lines are perpendicular to a line through the origin O. So suppose the direction cosines of the line through the origin O are L1, M1, N1. The direction ratio of the first line are alpha, beta, gamma. So because these two lines are perpendicular, so we have L1 alpha plus M1 beta plus N1 gamma is equal to 0. Similarly, L1 into A alpha plus M1 into B beta plus N1 into C gamma is equal to 0. And for third line, L1 into L plus M1 into M plus N1 into N is equal to 0. Now eliminating element, we have eliminating L1, M1, N1. It should be L1, M1, N1. We have determinant of alpha, beta, gamma, A alpha, B beta, C gamma, and L, M, N is equal to 0. Now take alpha common from the first column, beta from the second, and gamma from the third column. So we have alpha, beta, gamma multiplied by determinant of 1a L upon alpha, 1b m upon beta, 1c n upon gamma. This should be equal to 0. So expanding with respect to the third row, because we need L upon alpha, m upon beta, n upon gamma in the expression to be proved. So we have L upon alpha into c minus b plus m upon beta into a minus c plus n upon gamma into b minus a is equal to 0. Multiplying by minus 1 third, we get L upon alpha into b minus c plus m upon beta into c minus a plus n upon gamma into a minus b is equal to 0. This is what we are supposed to prove. Thank you so much.